So just a little review of what we have discussed so far in the topic of liquid-liquid extraction. The last two problems that I gave you as a sample, and the others, your assignment was actually based on those two sample problems. We're only tackling the equilibration of a mixture. A mixture of a feed, and then after the mixture has been homogenized, they were settled, and the two immiscible layers, referring to the raffinate and the extract layers, separated. Now that was our topic in the previous meeting. And now for this afternoon, we will be discussing a liquid-liquid extraction, wherein this time we will really have a feed, which is our LO, and it will be contacted with the solvent V sub 2. Now resulting to the equilibrated phases, the raffinate, which is V sub 1, and the extract, which is V sub 1, and the raffinate, which is L sub 1. So these two phases are equilibrated. Now, if we are to do material balance, that is overall material balance, mass balance for the separation process, then we need to add up all the streams that are entering the system and all the streams that are leaving, and it would be the sum of the masses of each of the phases corresponding to the mass also of the bulk phase M, where our interfacial surface where real mass transfer occurs. Now, our component balance, usually done based on solute A, is always based, the pattern is always based on your overall material balance. So what you only need to do is multiply each of the phases that appears in your overall material balance equation by the mass fractions of the corresponding phases. Now we will represent the mass fraction of the bulk phase M by X, just like we represent the mass fraction of the feed LO and the raffinate phase L1. Now our solvent V sub 2 and our extract V sub 1 will have mass fractions represented by YA1 in terms of solute A and YA2 for your solvent, okay, respectively. So YA1 is for the extract and YA2 is for the solvent. Now, we need not do a C balance because we are only allowed to use one component balance equation and one overall material balance equation. If we use this, then we will just keep on circling around the same values and we will be getting the same unknowns later on. So you only need one material balance equation, overall material balance that is, and one component balance. Now, as discussed in the introductory part of the topic, the sum of the mass fractions of each of the components in our phases should be equal to 1. So what is placed in here is only for the feed and for the raffinate phases. So that's X. But this same principle applies for the solvent and the extract phases. Now, when we have this case wherein you have already the feed and the solvent being contacted so that the solvent gets to extract A from the feed, when you do it graphically, although this is not the main purpose now or the main thrust of discussing this with you, you need to plot the feed right on the x-axis, just for your information. You can read this procedure in Jan please. And you need to plot the solvent, if it's 100% pure C, right on the tip of this triangle. Now, the bulk phase M will be somewhere between these 2 points that is forming a line. So your M is somewhere here. Now, your equilibrated phases, as shown here, the V1 and the L1, are actually formed out of the other, if you remember last meeting, out of the other rectangular diagram below, wherein from the raffinate phase here, we go down until we reach the curve, we turn left until we reach the line, that is the 45-degree line, and we go up until we reach the upper part of the phase envelope. The upper part of the phase envelope corresponds to the concentration of the extract layer, and the lower part of the phase envelope corresponds to the concentration of the raffinate layer. So you can see here that this is the tie line, signifying that these two phases L1 and V1 are equilibrated because they are linked or connected by the equilibrium diagram below. So if you recall last meeting, it's something like this one. So from the raffinate, you go down to the curve. This is the equilibrium curve. That is why we say these two are equilibrated. Then you turn left to the 45-degree line and you go up and rest on the upper part of the phase envelope. If you connect this point G, representing the extract, to the point I, representing the raffinate, you have what we call as the equilibrium tie line, representing that the two phases after extraction has already proceeded is equilibrated. So that's just a review. So in this case, this would be the construction of all those lines. So this would only be part of the discussion of extraction. It's not solely or wholly the focus of our discussion this afternoon. So it would only be part of the discussion. Now, in this sample problem, you're given a feed mixture weighing 200 kilograms of unknown composition. Now, the feed is containing water, acetic acid, and isopropyl ether. And it is contacted this time in a single stage extraction system with 280 kilograms of a mixture containing these percentages for the three components. So 40% for acetic acid, 10% for water, and 50% for isopropyl ether. You're given the resulting raffinate layer with the corresponding amount of 320 kilograms and containing 29.5% acetic acid, 66.5 weight% water, and a very little amount of isopropyl ether in the value of 4% by weight. Now you are to determine the feed mixture and the composition of the resulting extract layer for this particular problem. Now, this problem will use both the diagram and the analytical approach. This cannot be purely solved using analytical approach. And as such, at times, the student would say that the likelihood of this expected to come out in the board exam is slim. Nonetheless, the board exam is not the primary focus here. Our primary focus is that you learn, although we are preparing you for that. Okay, so this is our sample problem. So I'd like to change screen. That way we'll be able to determine what we need to determine in here. Now, I'll stop sharing for now because I need to share a different screen. Okay, so we're here now. So if we need to write what we are provided in the problem, so I will go back to the slide, but you won't be able to see it unless I again stop sharing and then go back to this board. You're given would be the feed, in this case, the amount of which is 200 kilograms with a known concentration. I'd like to go back to that. So your feed is 200 kilograms. Now it is to be contacted. Now our feed, by the way, if we are to represent it the way it's represented in extraction, it should be LO. So we will label this correctly as we would label it based on the representation in the illustration to you. Now, we don't know the composition of the feed, so we only know its amount. Now, we go to the solvent, I think, because the solvent is given. So for this problem, the solvent is given to be 200 kilograms of the mixture of 40% by weight acetic acid, and 50% by weight isopropyl ether. So if I know the acetic acid and the isopropyl ether, then the rest would be water. So recall that, ha? 40 weight percent acetic acid and 50 weight percent isopropyl ether. So I'll go back to that board and write here the given. So you have 280 here for the amount of the solvent. Now in here, since this is V2, its composition would be Ya2. And your A here is acetic acid. So if you recall, acetic acid, as I have read it a while ago, is 40%. Let me see. I may not
Yes.
get. Yes?
Yes, good afternoon, ma'am. Miss, wala ka ko imong aking share screen.
Okay, you're not seeing it. Wait, sorry. Share screen. Where is that? Sorry. Now you see my screen?
Miss,
Yes, miss.
Okay. So this is already the feed that I have written based on the problem. This is our solvent with this amount of acetic acid. I need to know the value of the isopropyl ether, and that's 50%. So I like to write it there as well. So your YC2 is equal to 50%. And your YB2, that's of water, is 0.10%. So we represent our composition as Y. A is our solute, C is our solvent, and B is water. Now, in our case here, our solvent already contains the solute that is in the first place to be extracted from the feed. And we are to determine what the problem requires from this. Now, aside from this one, you are given that the raffinate, so we know that raffinate is L1, and the value of that raffinate layer is 320 kilograms. So you have here 320 kilograms for this. Then we need also to determine its composition. So your raffinate is 29.5 acetic acid. So that would be A. So XA1, 0.295. And we can also write here XB1. And we can also write here XC1. But actually, we're only interested in A. But nonetheless, the problem gives that your water is 66.5%. So we'll go back there. So your water is 66.5% and your isopropyl ether remaining in the raffinate is 4%. So if you can check, this should all be equal to 1. Now let's see what the problem requires out of this given information. So giving us this information, we are to determine the original composition of the feed and the composition of the resulting extract layer. So in that case, we need to write that also in here. That way we know our we will have a sense of direction in solving this problem. So we need to know the composition of LO and the composition of V1, our extract. So your LO here will be, of course, XAO, XBO, XCO. Your V1 in terms of composition would be YA1, YB1, and YC1. So these are the things that we need to know. Given this information, we are to find this. Now, the easiest way to determine here is first, we need to come up with the composition of the extract because based on the composition of the raffinate and based on the principle that the two layers are equilibrated, we can get this right away from the triangle and the rectangular equilibrium diagrams. I'd like to go back to the slide, so I'll stop share and go back to the slide. Let me know if you cannot see. So we will go back to the triangle where we can get the value of the composition of the extract layer. So if you recall, if somebody was writing the given information, if you recall, our raffinate is to contain, let me see, it's to contain 0.295 acetic acid. Is that right? Our raffinate is to contain 0.295 acetic acid. I don't have anything to see here because it's not in the book. So is somebody writing it down? Is the composition of the raffinate 0.295 in terms of acetic acid? Hmm? Nobody? So then I need to escape because I can't remember. So our composition for acetic acid in the raffinate is the 29.5 weight percent. So in that case, we will have to find the 29.5 weight percent acetic acid in this case. So now, let me try this if I can write. Okay, you need to place in here the 0.295. You find this is zero point 0.5, this is zero point 0.4, this is zero point 0.3, this is zero point 0.2, and this is zero point 0.1. Your 0.295 is very near zero point 0.3. So let's say this would be that thing. I'd like to label this as L1. I have a difficulty writing there. This is L1. And what you're going to do from this point, you place it on the face envelope because our raffinate is right on the face envelope. It's not here on the horizontal axis. I only place it here so I can project it on the lower part of the face envelope. Then what you're going to do is go down. Where's that cursor? You go down here until you reach the curve. Then you go left until you reach the line. And then you go up. So this would be very hard. Just for sample illustration only. Let's say this is where we ended. I'd like to change this one. And this is, let's say, the point where we ended. So you go down, you turn left, you go up. Now the one you have here on top is your extract. So this must be B1. And that's it. Out of this point here, you can read the composition of A in V1. You can read the composition of C in V1 and then subtract the sum of the two from 1. That would be like your B in V1. So if I will not base it on what I have written, just based on my, shall I say, it's around, so if I'll go up, it's somewhere here actually. Okay, that's somewhere there. So I will estimate the value of A in that position for V1, and that would be around 0.12, or that would be 12% in A. Now, if this is 0.5, 0.6, 0.7, 0.8, 0.9, so this is 0.85 for C. So I'll go back to our solution. Stop share. And if we go back to our solution now, the first thing that you can answer is the composition of the extract. So for your V1, the extract that is, you can read YA1, which is more or less equal to, as I have said, 0.12. I'm not sure if it's that 0.12 because I only just made an estimation. So for C, YC1, that would be more or less 0.85 based on what I have also estimated. So your YB1 will be more or less 90. This is 97. So your B1 would be 0.03. So this is already the answer here for the composition of the extract. Okay, you're asked for the composition of the extract. So you only use the information of the composition of your raffinate. So in terms of finding the composition of the feed, you need to do component balance. So for your feed, so you will do component balance for the feed, and that would be LOXAO plus V2. This is your solvent, YA2 being equal to L1 XA1 plus V1 YA1. So the value that we have for LO is 200. So you will have a 200 here. We do not know this. And we have a V2. Your V2 is 280. So you have a 280 here. And this YA2, which is the composition of your solvent in A. So that's zero point 0.4. So you substitute it here. 0.4. Then your L1, which is 320. Your XA1, which is 0.295. And your V1, which is, what's the value of V1? Okay, V1, we do not know. So we'll let it as is. So V1 and YA1, which we have here, this one. That's your YA1. So I'll just place it here, 0.12. So since we still do not know your V1, so that we'll only have one left, one unknown left in this equation, we can do overall material balance. So I'll write it here on top so we can save space. So this would be LO plus V2. Your solvent is equal to V1 plus L1. Your LO is 200. Your V2 is 280. Your V1 is unknown and your L1 is 320. So from here, you'll be getting a value of V1, which is, let's see, I'm running out of time. Okay, so your V1 would be 320. Okay, 480 minus 320, it's 160.
Yes, miss.
So it's 160 kilograms. So you just have to substitute it here and you will have already XAO. Okay, the other manner of determining the C in this case will be the same as this one. You just change this to XCO, YC2, XC1, YC1. And then once you already have the two, you just add XAO to XCO. You add the 2 and subtract it from 1, you'll be getting XBO for us to save some time. So this is just the way you do it. But this problem cannot be solved purely using only the material balance equation. It is anchored upon the equilibrium diagram, the one that we base the composition of the extract layer. So the key in solving this problem is really using the principle that the two streams living, referring to the raffinate and the extract, are equilibrated, and their connection can be taken from the equilibrium diagram. So that's our sample problem for this afternoon for a single stage extraction system, wherein we only have one unit, and then we have separated already the layers and extract the corresponding component that we are interested in. Now, if I will stop share again here, that would lead me back to the one that we are. Do you see the screen? Using as guide. Okay, so this is our sample problem number 3. That's how we should solve the information, the required information original composition of the feed and the composition of the resulting extract layer. In a few minutes, class, I'll be disconnected. So we will just use the same link that we have been using. So I will just continue to make use of that time. So now our next goal for this afternoon is in the types of equipment for liquid-liquid extraction. The primary goal, yes? Yes? You don't see the screen. Wait, wait, ha. Wait. You see it?
Yes, Miss.
Okay. Okay na, Miss.
Okay, so this is already, that's already the sample problem number 3 solution. So we will now go to the next topic, which is the types of the equipments used for processing the feed so that we'll be able to extract the component from it. Now, in here, the primary principle used is flooding. That way, we can design our extraction column, meaning we can design how big it is, considering its diameter and how high it is in terms of its height. Now, unlike gas absorption, wherein the design for the height of the column is totally separated from the design of the, shall I say, the diameter of the column, because we also base it on flooding. This one, we can have one particular problem wherein both the diameter and the height of the column could be determined. So all we need to know is the shall I say, the HETS, which is also actually taken from a table. Once you have the HETS, then you only need the theoretical number of stages, or that it's the number of stages, and that's it. You have already the height of your column. So let's go now to each of the types of the uh, extraction equipment. So the simplest type is the one wherein we encountered in sample problem number 1. We have a feed that has been equilibrated and homogenized, and then the corresponding layers separated in the separator. So the extract and the raffinate are formed here, and of course the extract already has the solute from the feed. It could be a unit like this wherein you have a separate mixer and separator, but it could be something also wherein the mixer and the separator is only integrated in one unit. That is in the case of mixer settlers for extraction. Now, this one is a little bit complicated, but the thing is, in principle, the purpose is still to separate the heavy phase, which is your feed, and the light phase, which is your solvent, which already contains the solute from the feed. So this heavy phase here is your feed, and the light phase here is the solvent. So the heavy phase, which has already little of the solute remaining, is withdrawn at the bottom part, and the light phase, which is your solvent, which carries with it the solute from the feed, is withdrawn on top. It's the same as this one here, okay, in the previous slide. Now, we can also have the spray type of extraction tower, wherein the heavy liquid is introduced on top, and it is flowing countercurrent to the light liquid, which is sprayed against the heavy liquid that is going down. So your light liquid is bubbled up, your heavy liquid is going down. The heavy liquid is the feed, the light liquid is your solvent. So you have spray nozzles here at the bottom of your spray tower. Your feed that has already less of the solute is withdrawn at the bottom. So it's the heavy liquid outlet. And your light liquid solvent here is carrying with it the solute and is removed on top. That's in the case of our spray type extraction tower. Now, in the book, this one, your spray type extraction tower looks like this. It's snipped from exactly the way it's shown in Jean Couplis, your spray extraction tower. Now, this is used when we are expecting a rapid, irreversible chemical reaction to occur. in the case of neutralization of waste acids. The thing with this type of tower is it's limited only to at most two stages and it's rarely used. Though it's not costly, but it's seldom used. The tower that is most often used is the packed extraction tower because, of course, of its efficiency compared to the spray tower. Now, this is used when only a few stages is needed, but not as few as the spray tower, and with an interfacial tension around the value of 10 dyne per centimeter. So the choice of packing material is based on the continuous phase. Now, speaking of the continuous phase here, class, when we speak of the continuous phase, it's the feed. So in extraction, the continuous phase is the feed. So if you're using a pack tower for extraction, the choice of the packing material is based on the characteristic of our feed. Now in here, this uses preferably random packing over structured packing material. Just like in gas absorption, using random packing is more efficient than structured packing. Now, in gas absorption, we determine the HETP, if you recall. In here, we determine the HETS. So gas absorption is HETP, while in liquid-liquid extraction, it's HETS. Theoretical, the height equivalent to one theoretical stage. So how high is one theoretical stage when we determine the height of our packed extraction tower? Now, this one is greater, the HETS is greater than mechanically agitated towers. Those towers that have, shall I say, some form of agitation. Now, as I have mentioned a while ago, so the core, the base information or principle in which we are guided upon when we determine the diameter and even the height of our tower, extraction tower, is when it should be flooded. So I'd like to end here because the Zoom meeting is going to end in a little while, then I will just return. So flooding is an occurrence or a phenomena in extraction wherein both your phases, your heavy phase and your light phase, will live on the heavy phase region. So if I go back to the spray tower as a simple illustration for this, we have flooding when your heavy liquid together with the light liquid all lives in here. So no amount of liquid leaves the top of the tower. In that case, our column is said to be flooded. So that is based upon the description here of the flooding condition.